Can you see the screen?
Yes, we can see the screen.
Yes, we can.
Okay. So we were discussing the DC-DC converter. So DC-DC converter can be of two types. One is like isolated converter, another is non-isolated converter. In the isolated converter, you have to provide some kind of isolation between input and output side. And in the non-isolated, there is no isolation. Input and output, they are connected. So there are two major actually part of any converter. One is the switching network and another is the filter. So these two part comprised one converter. So this can be like buck converter, boost converter, or it can be buck boost converter. Okay, so if you look into the circuit diagram of a buck converter, this is the switching network and this is LC filter. And as you know that the filter, they reduces the ripple in the voltage and current. So inductor is used to reduce the ripple in the current, and the capacitor is used to reduce the ripple in the voltage. So voltage ripple is controlled by means of capacitor, and capacitor provides almost like a constant output voltage in a DC voltage. So in practice, there will be some ripple in the output voltage, but the amount of ripple depends upon the capacitor value. If the capacitor value is high, the amount of voltage ripple will be low, and if the value of capacitor is low, the ripple will be high. The inductor similarly controls the ripple in the current. And a high value of inductor means it will be almost constant current, and low value of inductor means you will have some kind of ripple in the current. So current ripple and voltage ripple, they are actually controlled by means of the filter element. So this is what we call a DC-DC buck converter. In the buck converter, you will see that the output voltage will be lower than the input voltage. Okay. So now what is the operation and how it works, that we will discuss here. So if you see that this is the resistive load circuit. So if this is the voltage that is in the form of pulses, then you will see that the current will be exactly of the same shape as that of the voltage. So that means it has huge ripple. The peak value is equal to the ripple value. And if you have inductance in the load, then the current will will be smooth, because there will be integration of the square wave, and you will have a smooth shape of the inductor current in the current. Now इसको तुम रख लिए थे क्या अपने पास? नहीं ये चाहिए बाबू, ये चाहिए, ये दिया उसने। और नहीं तो ये क्या, ये तो सिर्फ 50 रियाल का है, ये उससे मांगो जाकर, नहीं तो ये मेरा वो रिम्बर्स नहीं होगा। ये 270 + 50। हाँ तो इसका रसीद कहाँ है? यही रसीद है, ये ऐसा क्यों नहीं दिया? ऐसा इसके लिए 50 के लिए पता नहीं, वो 50 के लिए उसने ये बुक के लिए दिए, ये डोंगल के लिए दिए। अच्छा ठीक है, चलो हम ये अप्लाई करेंगे, अगर वो कुछ बोलेंगे तो हम बताएंगे। तो ठीक है, क्लास चल रही है। ओके, सो दिस इज द inductive circuit. Now let us see if we have RL circuit, then the capacitor, it blocks the DC and it allows only AC to pass, while the inductor, it acts as a short circuit for DC and it allows the flow of the DC component and it blocks the AC component. It offers impedance to the AC component. So that means the current ripple is reduced when inductor is connected in series. So now if you look at the inductor current conduction modes, so you see if the current You see, this is the current of the through inductor. This is the current through inductor. So this is called continuous conduction mode because the current is always positive and constant. Okay. Now, if you look at this third diagram, you see here the current reaches zero and then it remains zero for some time. It remains zero for some time and then again it rises. So since the current is zero for a considerable amount of time, this type of conduction we call discontinuous conduction. This is called discontinuous conduction because you have current positive for some time and then zero for some time. Okay. Now, if you look at the graph which is in between the continuous conduction and the discontinuous conduction, this is called the boundary condition for continuous current and discontinuous. So, continuous conduction mode is called CCM, and the discontinuous conduction mode we call it DCM. So the first one is the CCM and the lower one is the DCM, and in between what you see that the current goes to zero for a very just it touches zero and then again it increases. So that's the critical conduction. This is called critical conduction, or this is the boundary condition, because if the current stays for longer duration in the zero, then it becomes discontinuous. If the current is just above zero, then it is called it's called continuous. So this is the boundary between the continuous and discontinuous, and this is also called critical conduction. Okay. Now you see when the converter is operating in the boundary condition between CCM and DCM or critical condition, the ripple in the current is highest. The ripple in the current will be highest. If it is the continuous conduction mode, then the ripple is this. This is the current ripple. This is the current ripple. Okay, and your zero is somewhere here. But if it is critical conduction mode, then it will go to the peak and then come to zero. So this peak value will be, the ripple value will be high. This is delta IL. This is delta IL. Say dash. So the highest ripple will be seen when the converter is operating in the boundary condition. When it is operating in the boundary condition. Okay. So this is CCM, DCM, and boundary condition. Any question here?
All clear.
Doctor?
Okay. Now, yes.
Do we prefer like always CCM, or it depends on the application?
We prefer CCM.
Okay.
The DCM, when the DCM will happen, when your inductor value is too low, then the current drops to zero before the next pulse comes for the switching. So discontinuous is not a good mode. We want it to be operating in the continuous conduction. But whenever you design any whenever you design any converter, usually it is asked, what is the boundary condition? Means what is the value of minimum inductance that we have to keep? Because then if the inductance value is too low, what happens? You see, if it is actually, if you look into this, is physically what is happening when the current rises. Current rises when the inductor gets charged. When the inductor gets charged, the current rises. Yes. And when the inductor gets discharged, the current falls. The current falls. Now, if the inductor value is too low, what happens that it discharges very quickly. It discharges very quickly. So it discharges very quickly, and the current goes to zero, because all the energy is from the inductor is drained out. There is no more inductor energy is available to supply the current. So the current becomes zero, and still you have the time to switch the transistor or the switch again. So switching on is still you have time, because this from this to this time the switch was on, then from here to here the switch is off. So when the switch is off, the Inductor is supposed to carry the current and it's supposed to give the current to the load. But because it is very low value, it discharges very quickly. So the current drops to zero in a very short time. And that is why you observe the discontinuous mode. So the discontinuous mode happens because of the low value of inductance choice. So in the design, they usually ask what should be the value of the minimum inductance that you have to keep here so that you do not go to the discontinuous mode. So the minimum value will be of inductor will be obtained from the condition of the boundary condition, that is the critical conduction mode. So when we see the critical conduction mode, that is the point where the inductance value is the boundary value. So we have to keep the inductance value more than that, so that the converter operates in the continuous mode. Does it clear?
Yes, doctor. Thank you.
Okay. Now let us see the operation of the buck converter. What happens? This is the switch, and you give the switch on and then off. So the time for which it is on with respect to the total period, this is called the duty ratio. It's called the duty ratio. Okay. So the duty ratio can be maximum equal to 1. It can be maximum, Dmax can be equal to 1. So the maximum duty means all the time your switch is on. All the time your switch is on. When T on is equal to T, then you have D is equal to 1. So that means your switch is all the time on. When you have duty ratio half, that means the on period and off period are equal. On period and off period are equal. So this period and this period both are equal. Then it is called half duty ratio. Okay. Higher the duty ratio, that means the switch is on for long time and then off for short time. That is the meaning of the high duty ratio. Okay. So you design the converter for a particular duty ratio depending upon what is the input and output voltage ratio that you want. Okay. Or what is the buck, how much bucking you want, or how much boosting you want. Depending on that, you decide the value of D. Okay. Now, you see, this is switch, so it has two mode, either on or off. Now, what happens when it is on and what happens when it is off? So you see, when the switch is on, what happens? This plus goes here. Yes, this plus and this plus goes here. So this will be off. This will be off. This will be off. And the current will flow like this. So the inductor will get energy. It will get charged. So when it charged, the voltage polarity is like this, plus and minus, and the current goes here as well as the current goes here. That means the capacitor gets charged, the load gets the current from the source. So that's the situation when the switch is on. You see, in all the DC-DC converter, there are two things that is important. One is the current through inductor. Another is voltage across capacitor. However, you will see that, we need to know what is the current through inductor, what is the voltage across inductor, what is the voltage across capacitor, what is the current through capacitor. So these four things, current through capacitors. So these four things that you have to focus. So you have to understand what is the nature of the voltage, what is the nature of the current through the inductor and capacitor. And that is, you have to analyze in all the DC-DC converter, whether it is isolated, non-isolated, or the buck converter or boost converter. In all of them, what you need is the analysis of the current through inductor, the voltage across inductor, the current through capacitor, and the voltage across capacitor. Voltage across capacitor is actually same as the voltage across the load. Okay, voltage across the load, because they are connected in parallel. So we have, and you have to understand there are some basic things, that the average voltage across inductor is always 0. Average voltage across inductor is always 0, and average current through capacitor is always 0. So these points you should understand, and then you can analyze the circuit. It is very simple circuit. Just you have to you have one switch, and either the switch will be on or the switch will be off. Now, what happens to the inductor voltage and current, capacitor voltage and current when the switch is on, and what happens when the switch is off? That is all you have to look into when you are analyzing any DC-DC converter. So when look at this now circuit again. So there are two modes of this. One is when the switch is on, and another when the switch is off. So when the switch is on, what will happen that this diode will get plus and this will get minus, because this is how the source is connected. So the diode will be reverse biased. It will not operate. So the current will flow like this, and it will charge the inductor with this polarity. And when we charge the inductor, what happens? The current through inductor will rise. Current through inductor will rise. And this is how the capacitor current, and this is how the output load current. Okay. And you see the here the current that goes to the capacitor, this blocks DC. This blocks DC. So it only allows AC. It only allows AC. When it allows AC, that means the ripple of the inductor current is bypassed through the capacitor. The ripple is actually your AC component. Yes. So the AC component will be bypassed through the capacitor. So the ripple will, whatever is the ripple in the inductor current, that will be passed through the capacitor, and the average value of the inductor current will go to the average value will go to the load. That means the load current, which is equal to V naught by R, is also the average current of inductor. So the load current is also equal to the average current of the inductor, because the inductor DC component will pass, and the AC component will be filtered out by the capacitor. Okay. So this is the situation when your switch is on. That means the inductor is getting charged, the current is rising through the inductor, the ripple passes through the capacitor, the load current passes through the load, and the average load current we will see finally will be equal to your load current. Average inductor current is equal to your load current. Now, what happens when the switch is off? So let us see the switch off condition. Do you understand what is happening in the on?
Yes.
Okay, very good. So now let us see what happens when you have off. So when the switch is off, what will happen? That you see the current was flowing through the inductor. Inductor suddenly cannot stop current. It cannot allow sudden drop of the current, because current was rise up to some peak value. So it will not directly jump to zero. It will not jump to zero, but there will be slow fall of the current. So the current will start falling from the inductor, and you see this was now the inductor will release its energy, because it has already charged from the source. Now it will release the charge, so the polarity gets reversed. So the polarity gets reversed, so this become negative. So as soon as this become negative, this diode will be on. And you will have a current path like this. So there will be, source is not connected to the load side, but you will have inductor that is allowing the current to pass through the load and also through the capacitor, and the closed loop is through the closed path is getting through the diode. Now, what will happen to this current? Because you see the inductor is discharging. Inductor is discharging. There is no source in this loop. The only source is the inductor. The inductor is behaving as a source. So what will happen? And there is no input to this inductor. So what will happen? The inductor will, energy will release and the current will fall. Current will fall. Current will fall. And under a steady state condition, it will reach to the minimum value. It will reach to the same minimum value. And by that time, the switch is turned on again. So the current will rise again and then it will fall again like this. So you will have the current like this, the waveform. So this is the current form through inductor. Okay. Now, you see the inductor is pushing the current to the load. Inductor is pushing the current to the load. When the switch was on, there was current through inductor. When the switch is off, still there is a current through the inductor, and the inductor current is like this. Inductor current is like this. Now the ripple of this, all the ripple will pass through the capacitor, and the average current will go to the load. So the ripple goes through the capacitor because capacitor blocks DC. It do not allow the DC to flow through this. So where the DC will go? The DC will go to the load. So the load current will be the DC current, and that is nothing but the average current of the inductor. So you see, this is the average current. This is the average current of inductor, and this is same as your load current. The average current of the inductor is same as your load current, because inductor current has two components. One is the load component or DC component, and one is the AC component or ripple component. The ripple will pass through capacitor. Ripple will pass through capacitor. So that means whatever is the ripple, this ripple is same as your capacitor current. So you see, this is the capacitor current. All the ripple is, so just you have to draw the same nature. The same nature is that of the capacitor current, except that the DC value is not there. When there is no DC value, that means this current will be symmetric towards zero axis, because this was the offset. Yes, this was the offset. This was the offset. Now, when you remove this offset from the ripple, so what will happen? If you remove this ripple, if you remove this average value or the offset value, so what will happen? The whole curve will shift down, will be subtracted. So ripple, the capacitor current will be equal to the inductor current minus the load current. Inductor current minus the load current. So the load current is nothing but this offset value. So when you subtract the offset value, what will happen? The ripple will be now symmetric along the zero axis. So this is the capacitor current. Do you understand this part or not?
Yes.
Totally.
Now, you see, if we want to draw the input side current, so what is input side current? You see, when the switch is on, you have input current. Which will be same as your inductor current. Because this is the current that is flowing through inductor. But when it is off, then what is the input current?
Zero.
Yes. So when the switch is off, the input current is zero. And when switch is on, this is the same. This is the same. This part, positive part. And then, so this is your input current. You understand this?
Yes, doctor.
Now, let us look into what is the inductor voltage. We have to draw the inductor voltage. You see, capacitor voltage is same as your output voltage. Capacitor is same as output voltage. But what is the voltage across inductor? We have to see what is the voltage across inductor. So when the switch is on, this is minus plus, this is plus minus. Now you apply KVL in this loop. When you apply KVL in this loop, what you will write? Minus Vs plus VL plus V naught is equal to 0. Yes. So it is, yeah. So what is VL? VL will be equal to Vs minus V naught. Here, VL will be equal to Vs minus V naught. This is the voltage across the inductor when the switch is on. So when the switch is on, the inductor voltage is this. Vs minus V naught. Now, what happens when the switch is off? What is the voltage across inductor when switch is off? So when switch is off, you see, whatever is this voltage is same as your load voltage. Tell me what will be the voltage when the switch is off? What is voltage across inductor? Here it is
same as the load.
Yeah, but it will be negative because the inductor is discharging. The di by dt is negative. So it will be same as V naught, but negative. And also, you see, you know that the average voltage across inductor is always 0. Average voltage, remember this thing, always average voltage across inductor is always 0. So when it will be 0, you see, you have positive here. So you must have equal negative area. So the positive area should be equal to the negative area. Then only you will have the average voltage 0. Okay. And what is the this time? This is your on time, T on, and this is your T off. From here to here you have T off, and from here to here you have T on. So what is the T on and T off in terms of D? So you define D as T on by T. So you can write T on is equal to D into T. And what will be T off? T off will be T minus dt. So that means this is written as 1 minus T is equal T off is equal to T into 1 minus D. So this is how you write T on. This is how you write T off. So this time from here to here, this is dt. And this time from here to here, it is 1 minus d into t. Now the area of the positive curve should be equal to the area of the negative curve. So let us find the area. Let us find the area of the positive and negative. So the positive area will be how much? This voltage times this time. This is rectangle. So the magnitude, height, and breadth. So this will be Vs minus V naught times dt. That is the area. And what is the area in the negative side? The area in the negative side will be V naught into 1 minus d into t. We only bother about the magnitude, not the negative sign. So from here, what you can find? Simplify this. So this is Vs into dt minus V naught into dt is equal to V naught into t minus V naught into dt. So V naught dt cancels out. So what you have is Vs into dt should be equal to V naught into t. So t and t cancels out. So what you have uh, V naught is equal to D into Vs. So this is the relationship for the buck converter. The output voltage is equal to the duty ratio into the source voltage. Now, if you keep the duty ratio is equal to, say, for example, 0.2, the V naught will be equal to 0.2 of Vs. That means 20% of the input voltage. The maximum D you can go is 1. That means the maximum value of V naught should be equal to Vs. This is the maximum value you can get. But all the time you will get V naught less than Vs because your D is less than 1. So this is the operation of the buck converter. This is the operation of the buck converter. Any question here?
Doctor, regarding the voltage across the capacitor, won't it also like it will get charged and get discharged as well?
Yes, it will get charged and discharged. So what will happen that the voltage across, you see, ideally the voltage across the capacitor will be V naught, but it will be actually like this, some ripple. There will be some ripple. Okay, there will be some ripple, and this is your actual output. This is your actual output. The output will have some ripple. So value of capacitor is high. This will be more like constant. It will be more like constant. Okay, because capacitor, when it charges, the voltage increases. The voltage increases. The voltage rises. When it discharges, the voltage falls. So there will be rise and fall, rise and fall, rise and fall. So there will be like, the output will be like this, some ripple. But if it is high value, then it will give stiff output. That is very quick charge and discharge. So it will be like very fast, like this. It is very small, like small ripple. It will have, but practically it will have some ripple. You cannot completely eliminate the ripple. You can only reduce it by increasing the value of capacitor. So now all this I have explained you the operation of the buck converter when the switch is on and when the switch is off. So when the switch is on, the diode is off, the inductor gets charged, the capacitor gets charged, the load gets the current from the source. And when the switch is off, the source is disconnected, the inductor becomes the source, and inductor gives the current to the load. So it's the inductor that behaves as a source in this case. And this is the inductor current is a periodic current. So the inductor current follows this relationship. The average inductor current is always 0. The average capacitor current is 0. The power supplied by the source is the same as the power delivered to the load if we assume lossless components. If the switches assume to be lossless, the inductor and capacitor assume to be lossless, then we can say that whatever is the power that is supplied by the source is the same as the power that is coming to the load. The key to the analysis of determining the output voltage is to examine the inductor current and inductor voltage first for the switch closed and then for the switch open. The net change in the inductor current over one period must be 0 for a steady state operation. That means you start the current from here, it rises, the inductor current rises, it falls to the same value. This is the steady state condition. In the transient condition, you see it will go like this. It will go like this, like this. So it will not fall back to the same minimum value, and then finally it will reach the steady state. Then always the minimum, this is minimum, and this is maximum. The minimum and maximum will always remain same. And this is called the ripple, current ripple, delta IL, current ripple. So the average inductor voltage is 0. So the voltage across a inductor and the capacitor and the current ripple is obtained as this. So voltage across inductor we obtained is Vs minus V naught. And how you write the inductor voltage? You write this as L DIL by dt. So you can write DIL by dt like this. And then this rate of change of inductor current, you can write this as a small change in the inductor current. This is the current ripple actually. This is current ripple. This is the time. And then this total time is for one period. We call it on this because this is on period is dt. So this is dt. Then you can write the this is the the current rise. This much is the current rise. This much is the current rise, which is equal to delta IL under closed condition, and it is given as Vs minus V naught over L into dt. This is the inductor ripple current under closed condition. Now we find under open condition, when the switch is open, voltage across inductor is the same as the output voltage, but with negative sign because the current is falling. So we can write DIL by dt is equal to minus V naught by V naught by L. And from here you can write the current ripple equation under on condition, it is equal to this. But you see here, this was the on and now this is the off. But a steady state condition, the minimum and maximum should be same. That means this is the delta IL. So both delta IL should be same under open condition and closed condition. So the open condition and closed condition, you should have the same ripple. Of course, one is like going up, other is coming down. Now, when you equate these two equations, you get V naught is equal to Vs into D. And this is the equation that governs the buck converter. Now, the same thing we already derived, that this is the inductor voltage. This is the on condition, switch on, and here switch off. The area under this curve should be equal to area under this curve. So you find the area under two curves, and then you can get the same equation. Okay. So this is the equation for the output and the input. So thus the buck converter produces an output voltage that is less than or equal to the input voltage. So V naught is equal to D into Vs. So D varies between 0 to 1. So you can say that the maximum value of V naught can be equal to Vs. It is noted that the output voltage depends on only the input voltage and duty ratio. If the input fluctuates, the output voltage is regulated by adjusting D. So if the input is changing, but you want output to be constant, suppose you want a constant output, but your Vs is changing. So what you can do that, you can reduce your D, then you can keep the product constant. Or if Vs is going down, you can increase your D so that you keep your product constant. So this, you adjust the value of duty ratio if there is a change in the source voltage, so that you keep your output voltage constant. Okay. So a feedback loop is required to sample the output and compare with the reference and adjust the duty ratio. So this is the closed loop control. So how you do the closed loop control if there is a change in the input voltage. So this is the control technique shown here, that you have the reference voltage. And then you compare this reference with your output, so that the error comes here. And this is the PWM block, which compares the control voltage with the sawtooth or the triangular signal, and it produces the duty cycle. So it produces D, and then you have gate driver here that switches the your switch on and off. This can be your MOSFET switch or IGBT switch. Usually the switching frequency is kept high, 50 kilohertz to 100 kilohertz. So we prefer MOSFET for this application. And this is how the PWM signal is generated. Okay. Now, what is the maximum and minimum inductance current? So we can find the value of maximum inductor current, means this value and this value. Okay. because we know the ripple and also the average value of this, the average value or the DC value. The average or the DC value is nothing but I naught, the output current. We know the output current. We know the output current from V naught by R. So we know the average, we know the ripple, then we can calculate what is the maximum value and what is the minimum value. Okay. So the inductor current average value is same as the resistance current and it is equal to V naught by R. So the maximum current is equal to the average plus half of the ripple. Yes. This is your I naught and this is your delta IL. So this value will be half of the delta IL. Half of the delta IL. So the maximum will be equal to the average value IL, or you can write I naught plus delta IL by 2. This is your maximum value. And what will be the minimum value? How you get the minimum value? IL minus delta IL by 2. That will be the minimum value. Now, so the maximum value is V naught by R. V naught by R plus delta IL by 2. Delta IL equation we have already derived. So delta IL equation we have already derived as this. So we put that delta IL here. So you get this as your maximum value of the current. The minimum is same. You have already obtained delta IL. So you can put that here and you get the minimum value of the current. So this is maximum and minimum inductor current. Any question here?
No, all clear.
Clear, teacher.
Next is the conduction mode. So if your current is not touching zero, it is all the time above zero, we call it continuous conduction mode. If it touches zero and straight away it rises, that is called the boundary condition or critical condition. And if it rises but falls much before the switch is on, so there will be some current will stay to zero for some time. This is called the discontinuous conduction mode. So inductance value for continuous current. So you see, for inductance current to be continuous, the minimum inductance value you have to find out. So I minimum should be positive, because you see here, this is your maximum value, this is your minimum value. This is your minimum value of inductance current and this is the maximum value of inductance current. So the minimum value should be greater than zero. If it is greater than zero, I minimum, if it is greater than zero, that is continuous conduction. If I minimum is equal to zero, then it is critical conduction mode, because here also it will remain zero. So for continuous current, the I minimum should be positive. I minimum should be positive. But the boundary condition is when I minimum is equal to zero. That's the boundary condition. So to get the boundary condition, you put I minimum is equal to zero. So from this equation, you find the value of L minimum. So L minimum should be more than this value. Should be more than this value. Then only you will have a continuous conduction mode. Okay. Now what you see here, it depends upon D, depends upon R, depends upon the switching frequency. F is the switching frequency. So higher the switching frequency, lower will be the value of inductance. So in the design of the buck converter, the peak-to-peak variation in the inductor current is often used as the design criteria. Peak-to-peak inductor current is used as the design criteria. The value of the inductance can be found for a specific peak-to-peak inductor current. For continuous current operation, we have already obtained this equation. This is your ripple. This is delta IL. So delta IL is this. So the value of inductance is inductance. Okay, this is Vs minus V naught by L. This is from the on condition. This is from the on condition, and the value of L we can obtain as Vs minus V naught upon delta IL into F. Okay. So, okay. This is in general, they give you the inductance. This is the critical conduction mode condition. Okay. Here there is no delta IL, but here there is a delta IL term here. Okay. This is the value of inductance, how you calculate the value of inductance for continuous conduction mode. Continuous conduction mode. And if we assume lossless components, then the input power is equal to output power. So you can see that this is same as the ratio of the turn ratio of the transformer. You see, if you remember, V1 by V2 is equal to N1 by N2 is equal to I2 by I1. So similar is the case here. This is like turn ratio. You can assume this. This is just like equivalence of that. Now, how you choose the capacitor? So the output voltage is not perfectly constant. It has some ripple because you see, you have in the output, the capacitor is connected like in parallel with the load. So capacitor will charge sometime and it will discharge sometime. When it is charged, then it will discharge. When it charges, the voltage increases. When it discharges, the voltage decreases. So the same will appear across the resistance because they are connected in parallel. So the output here will be like this with some ripple. Okay. The output voltage ripple you can calculate from the voltage current relationship of the capacitor. So how we calculate the so what is the amount of charge that it takes in, and what is the amount of charge that it pumps back. So the amount of charge that it takes in, the same should be equal to the amount that of the charge that it gives back. So the current through the capacitor is IC is equal to IL minus IR. This we have already checked. This is your IL, inductor current. This is your capacitor current, and this is your resistance current. So if you apply KCL, you can get that IC is equal to IL minus IR. And IL is what? IL has a, you see, it has the output component plus it has that ripple. This is your load current. This is your inductor current minus the resistance current, which is nothing but the load current. So this is your IC. So you see, this and this cancels out. So what you have IC? IC is nothing but simply IL, delta IL. That means whatever is the ripple in the inductor, the same will pass through the capacitor only. All the average will go to the DC will go to the resistance, and the AC will go to the capacitor. Capacitor do not allow the DC to pass. So this is what you see mathematically also. When you apply KCL here, then IL is equal to IC plus IR. So you can say that IC is equal to IL minus IR. And IL is nothing but I naught plus delta IL minus I naught. So I naught and it cancels, so it is only delta IL. So this is the capacitor current. This is the capacitor current. This is exactly same as the inductor current. The only thing is that there is no offset. The inductor current, IL, you just subtract the offset, you get the capacitor current. So this is the capacitor current. Okay. Now you see here the current is increasing from here to here. I just discard this part because okay, even if you consider this part, from here the current is increasing. Okay, it is increasing, but this is negative. So I'll just, this is, you see, from here to here, this is one capital full. This is one complete cycle. This is one complete cycle. Like here, half is shown for the on period. This is the off period. Then you have on period. Then you have off period. So this is half of the off. This is half of the off, and this is on period. So the amount of charge that it will get during the on period, the same amount of charge it will give back during the off period. So just you can we calculate the the amount of charge that it will get during the charging period. That is my delta Q, amount of charge that it will get in the charging period. The same will be also, it will get discharged. When it get discharged, it release the same amount of charge. So we just consider half of it because both will be equal. Plus here delta Q, and here it will be minus delta Q. So both, because the sum will be 0 then. Okay. So just we see how much is the charge that it will hold during, or it will how much charge it gets when the current is input to the capacitor. So here you see current is rising, and then current, or you can say that current rising here, then fall here, but from here to here current is positive. Here current is negative, here current is negative. So when current is positive from here to here, positive current means current is coming to the capacitor and capacitor is getting charged. When the current is negative, that means current goes in the reverse direction. So when it goes in the reverse direction, the capacitor discharges. So now during the charge, during this period when the current is positive, how much charge it gets, the same amount it will discharge when the current is in the negative direction. Understand? So this is negative current, this is positive current. Do you understand this part or not?
Yes.
Perfect.
So what is happening here? We have to find out how much charge it holds, or how much charge it gets when the current input to the capacitor, or when the current is positive in the capacitor. So current is rising and falling, but it is positive all the time from here to here. So how much charge it gets? So to get the charge, we have to just find the area under this curve. We have to find what is the area under this curve. We have to find out the area under this curve. So, and you see, this is how the output voltage variation will look like. So from here to here, you see, from here to here, it is getting charged. It is not exact to the scale, but yeah, like this. So current, the voltage will rise when it charges, and voltage will fall when it discharges. So now we have to find out what is the area under this curve. So to find the area under this curve, when the current is positive, the capacitor is charging. When the current is positive, the capacitor is charging. So you know that Q is equal to CV. This is the relationship between charge, capacitor, and voltage. So the amount of charge delta Q should be equal to C into delta V. So delta V naught is equal to delta Q upon C. Now we have to find out the amount of charge stored in the area, shaded area. So it is half into base into height. Half base into height. That is the area of the triangle. So what is the half base into height? This is the base, half period, and this height is nothing but your delta IL by 2, because the total from peak to peak is delta IL. Peak to peak is delta IL. So half of this will be delta IL by 2. So this is delta IL by 2. So you can get T into delta IL by 8. So delta V naught is equal to T into delta IL by 8C. So from here you get the value of C. Delta IL is V naught. This is the formula for delta IL. So I will put this delta IL here. So the delta IL I put here, then I can find this as the expression, and from here I get the value of capacitor. So this is the value of capacitor. This is how you design the value of capacitor. Now what is this? You check. This is the voltage ripple. This is voltage ripple in the output. And this is the switching frequency. This is switching frequency. This is inductance value. This is duty ratio. Okay. So this is how you get the value of capacitor. Understand? Okay. So this is all about the buck converter. So here you see how you design the value of capacitor. What is the value of capacitor? Then here is the expression for the inductor. This is the inductor, and this is the minimum inductor for the critical conduction mode, and this is the expression for the min and max min current and max current. And that is all in the buck converter. So let us see the example. It says that the buck DC-DC converter has the following parameter. These parameters are already given. Assuming ideal component, calculate the output voltage, the maximum and minimum inductor current, and the output voltage ripple. So output voltage is D into Vs. So you simply get this. Everything is given. The maximum current is given by this formula. So you get this as the maximum current. And the minimum current formula is given by this. You get this minimum current. And then the last one, the average current is 1 ampere. The peak value is 1.5 ampere. So you can get the ripple in the voltage, which is 0.49%. So in the design consideration, most buck converters are designed for continuous operation. The choice of the switching frequency and inductance to give continuous current is this. So the value of inductor minimum should be more than this, and this is the value of the capacitor. Increase the switching frequency will cause a decrease in both L and C. As you see that here you have F, here you have F square. So if you increase the switching frequency, the inductance value will decrease, and the capacitor value will decrease by square times. It will decrease by square times. So this is what is mentioned here. When they increase switching frequency, reduce L and C, but the switching losses will increase because the amount of switching is large. So many times the switch is on and off. So the switch, there is more switching losses. So there is high temperature, increased heat sinks, lower efficiency. So this is the problem. But on one side, but on the other side, you get the reduced value of L and C. So on one side you have something, on the other side there is something, So you have to make a trade-off. So now some designers, they choose 500 kilohertz, the best compromise between a small component size and efficiency. Any question? Now other designer prefer 50 kilohertz to keep switching losses small, while still other prefer 1 megahertz. As switching devices improve the switching frequency, as switching devices improve, the switching frequency will increase. So that means, you see, before we used to have silicon only, now we have silicon carbide and gallium nitride devices. So these are high switching frequency devices because they have very less switching losses. Even when you have when switch it at in megahertz operation, they give less switching losses. So the choice of inductance, select L 25% higher than the L minimum. So L minimum you calculate and then you choose 25% higher. That means you multiply this by 1.25. Other criteria is that the inductor current ripple, which is kept about 40% of the average inductor current. So the ripple is about 40%. Smaller ripple means lower peak and RMS inductor current and lower RMS capacitor current, but requires large inductor size. So this is the another trade-off. The inductor wire must be rated at the RMS current, and the core of the inductor should not saturate for peak inductor current. Okay. So the capacitor must be selected to limit the output ripple to the design specification to withstand peak output voltage and to carry the required RMS current. The switch MOSFET with low on value of the drain to source and diode must withstand maximum voltage stress when off and maximum current when on. So the temperature rating must not be exceed often require a heat sink. So if you want to keep the temperature down, you have to have good heat sink design. So now this is based on one buck converter design. So design a buck converter to produce an output voltage of 18 volt across a 10 ohm load resistance. The output voltage ripple must not exceed 0.5%. The DC supply is 48 volt. Design For a continuous inductor current, specify the duty ratio, switching frequency, the value of inductor and capacitor, the peak voltage rating of each device, and the RMS current in the inductor and capacitor. Assume ideal components. So the output voltage is given as 18 volt. The input voltage is given as 48. So the duty ratio is 0.375. Switching frequency and inductor size must be selected for continuous current operation. And then you suppose you assume 40 kilohertz. So if you assume 40 kilohertz, the minimum inductor size, L minimum, will be 1 minus D into R by 2F. So you get 78. But you have to keep 25% higher value. So you just multiply 1.25. So this should be the value of your inductor. And for the average value, okay, now we have to calculate for the capacitor, we need to calculate the delta. This is given or not? You have to check if it is given or not. Okay. Now the average current and the change in the, so now this is the your load current. This is your load current. So the ripple in the current is Vs minus V. This is during on condition. On and off is the same. So this 2.88 is the ripple. So you can calculate what is max, what is min. So this is the peak value. This is the lower peak. So the inductor must be rated for RMS current, which is computed in chapter 2. And the RMS value of a triangular wave is given by this equation. IL square plus delta IL by 2 root 3 whole square. This is the formula for the offset current. The triangular for the triangular current. So this is the RMS value. This is the RMS value. And the capacitor value, this 8 into L, and this is 5%. This 5. This is given or what? The delta V naught by delta V naught. Yeah, 0.5%. Okay, the ripple is given. Delta V naught by V naught is given as 0.5%. So you choose this here, 0.005, and switching frequency 40 kilohertz. So you get 100 micro. So the peak current, peak capacitor current, because capacitor current is same as the ripple current. So this is delta IL, and this goes from 0. This should be from 0 axis. So this is the peak value. The peak value is delta IL by 2. This is the peak value of the capacitor. RMS of the capacitor from the triangular wave. This is the peak value divided by root 3. This is the same, peak value divided by root 3. That's the RMS for the triangular wave. So for a triangular wave, if you have a triangular wave, the RMS value is equal to the peak value divided by root 3. So peak value is 1.44 divided by root 3. So this gives you 0.83. Okay. Maximum voltage across the diode is 48 volt. Inductor voltage when the switch is closed is 30 volt. Inductor voltage when the switch is open is 18 volt. So therefore the inductor must withstand 30 volt. Capacitor must be rated for 18 volt output. So this is all on the design. And here it is computed for the triangular wave. So you have to know that for the triangular wave, the RMS is given like this. Okay, the RMS for the triangular wave is Im by root 3. But here you have the for the inductor you have some offset. You have some offset. That's why this offset is added here. Now next is the continuous conduction mode. So if the inductance value is such that the current drops to 0 before the switch is on, this is called discontinuous mode. Analysis of discontinuous mode is different. The relationship between output and input voltage is determined by first recognizing that the average inductor voltage is 0. So this is the on period dt or dt, but it falls before the switching period t. So suppose this period is d1 by d1t. Suppose I assume this as d1t, because from here to here it is 1 minus d into t. This was off in the normal continuous mode, but here you have to write this as d1t. Now we have to solve this to get the value of d1. We have to get what is the value of d1. So to get d1, average inductor current equal the average resistor current, because the average capacitor current is 0. This we know already. So with the output voltage we assume, so this is the average inductor current is same as your load current. So the average current, average inductor current, IL, we obtain as average inductor current, we obtain from here, the average value of this. IUL average. So you see, this is the area. You see, you find the area under this curve, divide by t. That's the average. This is how you get the average. The 0 to t into IL dt. This is how you get. So from here to here, you take the average. Then from here to here. So this is the area under this triangle, and so this is half I max into dt. This is area under positive, not positive, but both positive here, rising. So in the rising, this is the area. This is the area under rising, and this is the area under falling. Divided by 1 by t, that gives you the average value. That gives you the average value. So that gives you the average value. So this is the average value. This is the average value. And this should be equal to V naught by R. So you come make this equal. And now this is the voltage across inductor. When it is on, this is Vs minus V naught. And when it is off, it is minus V naught. And from here to here, it will be 0 because it is not conducting anything. So it is 0 here. So now for this waveform, again, we find this area, and the sum of the two areas should be equal to 0. So you do the same thing. So from here, this is the area under positive curve, this is the area under negative curve. When you equate them, you have this. So from here, you get V naught by Vs is equal to d upon d plus d1. Okay. So now you have these two equations, and we will see how we solve this. So since the current starts at 0, the maximum current is the same as the change in the current over the time when the switch is closed. With the switch closed, output voltage of inductor, we already know this, that this is the voltage across inductor. So you find this is the same as this IL max and everything. Now I already calculated this thing, and the boundary between the continuous and discontinuous conduction. This is the boundary condition. Okay, this is this. Okay. Now solve for. So put Imax in the following equation. Put Imax in the following equation. Imax I put here. Yeah, when I put the Imax, I put the value of Imax here. What I get, we get this as the quadratic equation. We have to solve this quadratic equation to get the value of d1. Once we get d1, you put here d1, and once we put here d1, we get this as the equation for V naught. So this is the final equation for V naught. So you see, in the continuous conduction, it was simple. This was only d into Vs, but now it is this. Okay. Any question here? So when you have discontinuous conduction mode, our aim is to find out what is d1. And after finding d1, our aim is to find out what will be the V naught. So the d1 is found like this. This is d1. This is how you get d1. And after getting d1, you can get the value of V naught. So this is V naught. Okay. So now you can see V naught. This is 2d upon d under root d square plus 8l by RT. So it is in terms of d. There is no d1 because d1 we already substituted here. Okay. So this is called discontinuous conduction mode. And based on that, you have just direct substitution problem here. So Just I'll finish this by discussing this last thing. This is called synchronous buck converter. What you do that, in the normal buck converter, you have a diode here. Normal buck converter. But diode is considered, very lossy component in any power converter. So the most loss that takes place is in the diode. So now if you replace this diode with a switch, then this is called synchronous buck converter. So this type of converter we use in battery charging applications. So this works as a buck converter, but the only thing is that it improves the efficiency. Improves the efficiency. And you see what happens here, that from the PWM signal, you apply to this switch and you apply the inverter of this switch. So that means when this is on, this is off. And when this is off, this is on. So the complementary operation. And the same thing was happening when you had diode. So the same thing you put here in the with the switch. So only thing is that you replace with the switch, you get higher efficiency. That is called synchronous buck converter. Okay. So we will take up the boost converter in the next class. Now regarding your the midterm exam, the makeup midterm exam. Makeup midterm is only for those who